Let's prove that there are an infinite number of prime numbers. And if we look at the syllabus, this does come up under the proof by contradiction section. So this is something that you do need to be aware of. It will be in your textbook too. But I'm going to try and explain it in a bit more detail just so you understand how it really works. So as the syllabus says, this is a proof by contradiction proof. And the idea of proof by contradiction, you assume that the quote opposite conclusion in the question is true, right? So the conclusion in this question is that there are an infinite number of prime numbers, right? So what is the opposite of that? Well, there are a finite number of prime numbers. So your first sentence is going to be this. To the contrary, assume a finite number of prime numbers, right? So essentially what that means is that prime numbers don't go on forever. There is a final prime number. So what this means is that there are n primes, where n is some whole number, right? So we've got n primes. So this means that we have n prime numbers, and we're going to call them P1, that's the first prime number, P2, that's the second prime number, P3, P4, all the way up to our final last prime number, Pn. So obviously that just means P1 is 2, P2 is 3, right? Because remember, 1 is not a prime number, so the first prime number is 2, just remember that. Now, the trick for the next step of the proof, and you just have to know this, unfortunately, this is just something that you just have to know, is you're going to let capital P, this capital P here, be the product of all of these prime numbers before, right? So times all those prime numbers together, P1 times P2 times P3, all the way up to Pn, and then you add 1 to it, right? So that's your trick for the next step. Apologies, quick little commercial break. If you go to the link in my bio, you can tick which topics you want me to cover for my A-level maths group webinars. I have mentioned this before in a couple of previous videos, but I am going to be running in the near future group A-level maths revision webinars for different topics in the syllabus. Click the link in the bio, tick which topics you want me to cover in those webinars, and the most popular topics are the ones that I will do, and then I'll get those set up. You can buy your tickets for £5 to join the webinar. So do that if you want to. Now, going back to that proof, remember from GCSE that you can write numbers as a product of prime factors, yeah? You remember doing your factor trees and products of prime numbers. So any whole number, any positive whole number bigger than 1 can be written as a product of prime numbers. So basically, prime numbers go into every number. They're like the building blocks of numbers, right? Or the atoms of numbers, yeah? So this capital P is obviously an integer, right? It's a whole number because these are all whole numbers and we've added 1 to it. So I know for a fact that a prime number must go into this capital P, right? Because I know from GCSE that I can write any number into factor trees. So I know that there must be a prime number, and probably multiple prime numbers, that go into this P there. I know that must be true. So I know that there exists a prime number, and I'm going to call it Pi, right? So P subscript I. There's going to be a prime number that goes into this capital P. So a prime number Pi that is a factor of this capital P. So to finish off my sentence, there is going to be a prime number Pi that is a factor of this capital P, since any integer greater than 1 can be written as a product of prime factors, because we know that from GCSE. So what that means is that this big P there, this big number P divided by this prime number must be an integer, okay? If this prime number goes into P, well, obviously when you do this big number divided by the prime number, you get a whole number because Pi goes into it. So now what I'm going to do, I'm actually going to try and calculate what this is. So I'm going to go back to this original kind of equation here and divide everything by this Pi. So I've just rewritten this formula here and I've divided everything by Pi. Now, what I've just done here, I've just split the fraction into 2, right? So the first fraction is this part here, and then the second fraction is 1 over Pi. Now then, this Pi is one of these prime numbers, okay? Because remember, there are a finite number of prime numbers. That's our assumption with this proof, right? So this Pi is somewhere in this list, okay? This Pi is a prime number. This Pi is part of this list of numbers. So what that means is that this Pi is one of these factors. It's one of them, right? It's one of these numbers somewhere in this list here. Doesn't really matter where this Pi is. Let's just say it's somewhere in the middle, right? So you've got P1, P2, P3, and then somewhere in the middle is this Pi. So what's going to happen with this first fraction? Well, the Pi is just going to cancel out like that, right? So now we're left with this product of prime numbers missing the Pi. I'm just going to write a note here to say that this is missing the Pi. So Pi no longer exists in this product of numbers here because now Pi is cancelled out. So you've got this product of numbers here plus 1 over Pi. Now, this product must be a whole number. Agreed, right? These are all whole numbers. Obviously, they're prime numbers, right? So this is going to be a whole number. Now, 1 over Pi, right? Is that a whole number? No, because every prime number is bigger than 1. You've got a whole number plus 1 over a number, right? So you got a fraction, a rational number. So hopefully you can see that this is not an integer. Yes, so this is not an integer because that's a whole number plus 1 over, could be 1 over 2, 1 over 3, 1 over 5. That's not an integer. Now notice how this contradicts what we said up here, right? Because pi was supposed to go into this capital P, so this is supposed to be an integer. We've just found now that it's not an integer. This is a contradiction. So that's a contradiction. So if we do get a contradiction, it means that our assumption at the start must have been wrong. So that there must have been wrong. There cannot be a finite number of prime numbers. There must be an infinite number of prime numbers, and that's the proof. Now, to be fair, I highly doubt they're going to ask you to regurgitate that proof in an exam because you can literally just regurgitate it and do that. But what they could ask is they could ask you parts of the proof. So in a question, what they could do is they could say, let capital P be equal to all of this here. And then they could ask you to determine whether this is a prime number or not. And what you'd do is a very similar thing to this here, where you'd say, well, okay, if you divide it by pi, well, you're going to end up with something that is not an integer. So therefore, this must be prime. So I doubt they'd ask you to regurgitate it, but if you know the proof, then you can answer a question like that pretty easily.